Okay, let's continue. Please, could you please close the door? So in the last hour we talked about a probability space which in all generality has this form omega r p, where omega is the outcome set, R is the sigma algebra on the outcome set, and P is a probability measure on the sigma algebra. Why did we talk about that? Because random variables are defined on probability spaces, and random fields are defined in terms of random variables. The other way around, random fields are defined in terms of random variables. Random variables are defined in terms of probability spaces. So this is the hierarchy and the sequence of things that is necessary to understand what a random field is. So this is why we have to at least establish a very little bit about probability spaces. We've also seen an example, which was the classic die experiment. For anything else, you can contend with what we discuss in the script, but you can also, of course, read around on Wikipedia or wherever to learn more about probability spaces. The thing is, probability spaces, as long as the omega is discrete and finite, so that you have, like, let's say 10 elements in there, which of course in real random experiments you might sometimes have, like if you have, I don't know, 10 times of marbles in a bag and you draw something like that, then things are fairly straightforward. You can always take the power set as the sigma algebra, and then you need to define your probability measure. The things get more complex, let's say, if omega is infinite continuous. So let's call it continuous infinite. For example, if omega is the set of real numbers, or if omega is the set of real valued n-dimensional vectors, so the stuff that we dealt with also for the GLM. In this case, for the sigma algebra, you cannot use the power set anymore, because you need to then use the sigma algebra, and this really goes deep into measure theory to understand why this is the case. So we don't have to deal with it here. So you can essentially think that even if in the real, if the outcome space is real valued or n-dimensional real valued, the sigma algebra, which in this case then is the standard one that is always chosen, is maybe different, is the something like this, is the so-called Borel sigma algebra, which is constructed in a fairly specific way. This is the proper sigma algebra for the real numbers. You can, nothing bad will happen. You can always view this as the power set of the real numbers if you, to at least associate something with it. Yeah? So if you think a sigma algebra for the real numbers is the power set of the real numbers, nothing bad will happen. You just will be wrong, but that's, at least you associate something, and you're not like, Borel sigma algebra, I don't know what it is, I can't associate something. So this is just one thing that I'm mentioning here. I also wrote about it. We will actually, we will see it sometimes, but not very often. The whole thing, and this will become clear once we talk about random variables, the whole thing about these probability spaces is that from an applied perspective, they are actually shoved behind something where you don't look. So they are behind a wall and you don't look there. They are there, but you don't look. You focus on something else, and or shoved, not shoved, shoved there. And so there is there might often be a Borel sigma algebra, but you will not talk about it, and so you also don't need to worry about it. So this I'm just mentioning, the Borel sigma algebra. And yeah, I think I stop here on probability spaces and focus now on random variables. We will see the Borel sigma algebra again. Think of it as a power set of the real numbers or the multi-dimensional real numbers, but yeah, so that you associate at least something. So again, we're doing this whole thing because we want to define a random field as a collection of random variables. So we now really need to talk about random variables. And the associated concept of a distribution. So I think the best mnemonic to study and learn and memorize what a random variable is to memorize that a random variable is neither random nor a variable. So a random variable is a specific type of function which I call x here. So the random variable is called x. From omega, of course, this you should keep in mind that in the background we now always have our probability space. So we have somehow a probability space defined, and this omega refers to the omega of a probability space. So a random variable x is a mapping, a function like x squared or exponential of x or something, from the elementary outcome set to another set, which I call gamma here. And what we are particularly interested in actually is the case of real-valued random variables. So that means that the random variable is a function from the elementary outcome set to the real numbers. Yeah. Essentially, it's just a function from the outcome set to another set. But mainly, when talking about random variables in mathematics, people usually associate with the notion random variable. They associate a real-valued thing with the notion of a random vector. They associate an n-dimensional thing, and then somebody had generalized that to, was it called a random entity or something, so that you don't always have to dissociate between random variable that is only one-dimensional and a random vector which is n-dimensional, but you can treat them as one class, which makes a lot of sense. Personally, in this case, I don't care that much, so I'm happy to call something a random variable also if it's a multi-dimensional outcome, because but the real mathematical random variable is always a one-dimensional thing. So what does that mean? Well, it means, like, for function, it takes an element of its domain, so an elementary outcome in this case from the outcome space, and maps it to a value, which is called x omega, and this is a real value, right? So you can, if you can't help but visualize things, I'm not convinced that visualization always helps, but sometimes it helps. But if you can't help to visualize this notion of a random variable, you can think of it like you have some elementary outcome space omega here, and for example, the discrete set that we just saw, the numbers 1, 2, 3, 4, 5, 6, or something else like the real numbers or anything, a set. X then, if it's a random variable in the strict sense, so a real valued random variable, takes elements here and maps them onto values on the real line. So this would be an x omega, and here that's the omega that's taken there. So that's a random variable. Yeah, a random variable is a function from the outcome space to another space, usually the real numbers. Functions, are not, that functions are not random. Yeah, functions are deterministic. So if you think of the functions that like x squared, 2x, or exponential of x, there is no randomness. Once you know x, you know the value of the function. Yeah, and this is exactly the same kind of function. Yeah, so there is no randomness here. This is why random variables are not random, and they are also not variables, because I don't know what variables really are, but these are functions. So they are not variables. Yeah? So random variables are neither random nor variables. They are not any kind of function, though, and this we have to specify a little bit more, because they need to be what is called measurable. And this is something, so in mathematical literature, you will always read about measurable functions. They mean random variables, or most of the time they actually mean random variables by that, but it's more precise, and they use this as if they're treating random variables in a mathematical context, they usually call them measurable functions. And this is not very important, that you get this framework, not so much the meaning of measurability, but how this thing of a probability space, a random variable, and your intuitive notion of what a random variable is, how these things go together. To do that, we first have to talk about what is known the preimage. Maybe you've seen that in the script previously, what a preimage is in terms of functions, but I'm not quite sure. It's relatively simple what a preimage is. So the way it works is as follows. Let's say we're dealing with a real-valued random variable, and say we have a set S that is a subset of the real numbers, for example, an interval. Yeah, so an interval from A to B. So here, this thing, A, B. That's a subset of the real numbers. It's not all the real numbers, it's just a subset. And we call this S. Let's assume we have that. Then we can talk about what is known as the preimage of this set of the real numbers under X. And what that means is, and this is something one just needs to memorize, and then it's fairly easy, these are the omega in omega for which X omega is in S. Yeah, that's called the preimage. So these are the elements in the domain of the function, which in this case is the elementary outcome space, that map onto elements in S. So again, maybe let's visualize that. Let's say this is our S, and we have a couple of omegas in here. Then we immediately see that that this thing here and the associated omega, so omega 4, is not in the preimage of S, because omega 4 is mapped to this value here, which is not in the preimage. About these other omegas we don't know yet, because I haven't said anything about them. So let's assume that X maps this thing actually into S. It also maps omega 2 into S, but again omega 3 is mapped somewhere else. So then at least omega 1 and omega 2 are parts of the preimage of X. The preimage of S under X. Yeah. So very roughly, of course, these omega 1 and omega 2 are elements in the preimage of S. So more generally, so you first define a set in the range of the function for example, the real line or the real or the n-dimensional real vectors or anything, whatever your space is where your random variable maps to. You define a subset, and then you think about the omega in the domain of the function, which is the elementary outcome set, that map onto elements of this S. Yeah? So that's the preimage. Now, this preimage here is, by the way it's defined, is a subset, or maybe it's actually the whole thing of omega. Yeah, so it's because it's defined like that. So it's the omega in omega, so the small omega in omega, the elementary outcomes in the elementary outcome set that map onto elements of S. Now we talked about how the probability measure assigns probabilities to subsets of the outcome space omega, right? So we talked about that the probability measure P that we discussed is defined as a function from the sigma algebra to the set 0, 1. Yeah. Now, what we actually want to do is to assign a probability measure to these preimages of random variables. Yeah, so these preimages, they are subsets of omega. We have a probability measure that assigns probabilities to subsets of omega. So let's maybe assign a probability to preimages of our random variable. To do that and to be able to do that, we have to be certain that the preimage of a set that we are interested in is actually in the sigma algebra, because otherwise, if it's not in the sigma algebra, there is no probability measure associated with it from the definition and the setup of the probability space. Yeah? So one can define then a measurable function as a function such that all preimages, which are sets, are elements of the sigma algebra of the underlying probability space for all subsets of let's do it like this first. Subsets of, in this case, the real numbers. Yeah, let's do it like this. One can then mathematically actually establish that this kind of setup works if one also has a sigma algebra on this set here. So this needs a little bit of mathematical formalization. So the sets that one actually wants to consider the preimages of, they also form a sigma algebra if one uses this setup. But this is not particularly important. It's more important that that we can be sure in this setup that the preimages are actually in the sigma algebra. By definition, yeah. So because we're only considering measurable functions, we're considering only those functions for which the preimages are actually in the sigma algebra. Yeah? And we're just doing this little bit of technical fiddling to be able to actually associate now a probability to preimages. So let's do that. So that was a little bit of a fiddly, but now because we have measurable functions for all S, which are subsets of our space with the random variable maps, we can define the following, and this is now really important. So we can define what is known as the distribution of a random variable. Sounds very familiar, the term. Now, a distribution of a random variable is a function from a sigma algebra of sets, which are these sets S here, to 2, 0, 1. So each S gets allocated a probability P underscore X. And the most important thing follows now. This is defined as the probability of the pre-image of S under X, which is by definition the set of the omega in omega for which X omega is in S. Yeah. So this is really the crucial thing here. So the whole setup is designed that this works. So by defining a measurable function, you ensure that these pre-images are actually measurable, so that you can actually allocate a probability based on, of course, the original probability measure here to these pre-images, and this probability that you allocate to the omega and omega, which get mapped onto elements of S, this is what you call the probability of the set S under X. So that's the probability that is associated with a set S under X. And this is, of course, also a probability measure. I mean, it's not completely clear that this is a probability measure, but one can quite simply show that this is not simply, but one can show that this is also a probability measure. By construction, it's very intuitive that it's a probability measure because it's just basically ripping off the original probability measure. And this probability measure, this Px, this is called the distribution of the random variable. Yeah? So the distribution of a random variable is a probability measure that is defined in terms of the pre-images of the random variable and the underlying probability measure of the original probability space. What this then induces is a second probability space, and I make this concrete now maybe I make it very concrete for one setup so that you know what we're talking about. Well, these are the days that I've spent in prison so far. Let's make this really concrete, this whole setup. So let's say we have a probability space omega RP. Now it's getting slow. What's going on? Don't know. And we define a random variable on it. We define X that takes elements from omega and maps them into the real numbers. This induces, by construction, with the definition of a distribution, this induces a second probability space, namely, somehow it's really getting slow, my machine here, maybe because I'm synchronizing. This induces a second probability space that has as elementary outcome set the real numbers. As sigma algebra on that, we take the Borel sigma algebra that I just mentioned earlier briefly. And more importantly, it has, as probability measure, it has the distribution of X. Yeah? So the distribution of the random variable X. So we have a second probability space here. And these are the probability spaces that we always talked about last term. Yeah? So we talked about something like Px, which was the probability distribution of X. Most of the time we actually meant the probability density of X, but yeah, we left it kind of unspecified, like like it's done in non-mathematical subjects like machine learning, for example, where I got this from, so from the machine learning books, and sometimes also in applied statistics. But these things that we discussed last term in some depth, these are the things that we constructed now mathematically a little bit more rigorous. Yeah? So this is the same thing. So when we talked about probability distributions of random variable x and wrote it like small p of x, what we actually meant, as we understand now, is the probability distribution of x, which is defined in terms of the probability measure of an underlying probability space and the preimages of the random variable. Yeah? That's how the mathematical setup is constructed. So where is the notion of randomness then in this whole thing? Because I said these are functions and there's nothing random happen. Actually, this kind of way of talking about probability and randomness, they actually don't talk about randomness. So you can also, I started to look into this original Kolmogorov thing from 1933, or in English 1956. It's actually not that hard to read once one knows these things maybe, but it's straightforward because it also makes explicit this kind of divide. On the one hand, you have mathematical formalization and functions and sets. On the other side, you have these intuitive notions of randomness and something random happen, and it is fairly explicit about this and says, now this maps onto this maps onto this, and we only care about the mathematical theory here. But how does the randomness come about here? The intuitive idea is that, again, like for the die, we have the elementary outcome set with our omegas in here. So they are all different omegas. And then there is a probability measure on this elementary outcome space, which is our P. And then, like we just discussed from for the die experiment, based on the definition of this probability measure, we can draw an omega from the elementary outcome set at random, but in accordance with the associated probability measure. So, for example, for the die, it was that the elementary outcomes have 1/6 for 1, 2, 3, 4, 5, 6. Let's say we have an unfair die where 1 is much more probable than 6, then we could use a different probability measure. For example, I don't know, 1 gets 1/2 and 2 gets 1/3, and we'll just make sure that the whole thing is normalized. According to this probability measure, we now draw something from the elementary outcome set. So we get a realization here. Let's call that omega E. This omega E is random because it was randomly drawn, and this then gets mapped onto a value x omega E, which is, the mapping is deterministic, but of course the omega E was random. So what we see as the values that the random variable takes on, they also, if we follow the setup, they also appear random because this was random. But they are random in a way that we can reconstruct if we know what the function does and what the underlying probability measure was. And this way of reconstructing what's actually going on, that is called the probability distribution. Good. Questions about the setup. So it's relatively intuitive, I think. It's the complication that is put in is that the random variables are functions. They are deterministic. But and then the complication maybe is this measurability and Boole sigma algebras, but there you won't try to relax with the measurability, just say, okay, it's just so that it's definitely, we can assign something from our original probability measure with the Boole sigma algebra. Just think of it as a set of sets. How exactly this is constructed, that's really not that important.
You said, so this notation here, P, X, like the one you used before, is this equivalent to what you wrote down there?
This here?
Yeah, because is it the same X as the function X there?
This here?
No, the one of the
This here, yeah. Maybe let's make that more explicit, because I assume some of you are familiar with this notation. So this so maybe just to discuss it again. So here we said that's a random variable which has a probability distribution / probability density. And we were never specific. Now we are much more specific of what a probability distribution is. A probability distribution we defined here explicitly in terms of the preimages of random variables. We haven't discussed at all what a probability density function is or what a probability mass function is. So currently we're just talking about probability distributions, and in the measure theoretic world of mathematical probability theory, probability distributions are probability measures. Yeah? So they are functions that are defined on sets, so they allocate values between 0 and 1 to sets. Here, in the machine learning world or whatever, one is just not specific about it, and one doesn't consider, one doesn't really say, I mean, this is one of the questions, I think, of the study questions, what is the meaning of this? And I have some discussion about this. It's not really clear what the meaning of this is. But, so if you read mathematics, mathematical stuff, then a random variable is a deterministic mapping. And you can, and this is why it's not a big problem, for example, in machine learning or for everything that we did in the winter term, because you can always construct this, what I've just shown you, that the random variable is a mapping and that there's an underlying probability space. You can always, if you want, you can always construct that once somebody told you, yeah, X is normally distributed, then you can go about, okay, so what does that mean? And most of the time, and this is also what's a little bit confusing. So what that means, if somebody says X is normally distributed, they are actually referring to this. So they're referring to the probability distribution, which can describe a probability density function, which is of the Gaussian form. There you then can, if you want, invent an underlying probability space that has a probability measure that then results in the fact that this is actually normally distributed. And the easiest way to do that is to say, if you want to make your life really simple, then you say, yeah, okay, let's invent an underlying probability space, and let's define a function. Let's say X is the identity mapping, and let's say our elementary outcome space are the real numbers, and the measure that we define on it, we define in terms of a probability density, and for this probability density we take the Gaussian distribution. So then you just duplicated this, but you still have invented an underlying probability space. You also can do different things, and that's where the power then comes. For example, if you're interested in setting up random number generators, and you say, okay, I want to create a random number generator that creates samples from the normal distribution. But I only have a chaotic system that generates things that are uniform distributed. So then you have to think, what kind of mapping do I need that renders something that is uniformly distributed, something that is Gaussian distributed, so you will come up with a more interesting mapping that X, that's a more interesting random variable. So the whole thing about probability spaces and things behind the things that you usually consider is they are models, so they don't exist. And the other thing is you use them for a purpose. Yeah? So you will not, if we are talking about if there's no purpose to invent this, for example, last term there was no purpose to invent now a probability space behind our normal distribution. So we didn't do it, because why should we? I mean, we can, but you don't need to do everything that you can, as you might have figured. So, yeah. So this is why these two kind of conceptualizations are both there. The problem that always happens with this thing is if things get more interesting in the sense that you need to be more specific. Am I talking about a discrete random variable? Am I talking about a probability density function? Am I talking about a distribution? Can this random variable, can it have a discrete distribution and so on? In this case, then it starts to be helpful to invent and explicitly discuss the underlying probability space, because there you have a model that encompasses and can be adapted to both the discrete and the continuous case. Then it's when it's really powerful. So this is the first time that I really actually needed that. Was when we did with Ludger this thing that we view maximum likelihood as a special case of restricted maximum likelihood, as a special case of expectation maximization, as a special case of variation at base. In this case, we needed the idea that we have a Dirac distribution, so that a specific value has probability 1 and all the other values have probability 0. There we had to mix together discrete and continuous distributions, and there you find that in the supplement of that paper, we needed to invent a probability space to make the whole thing coherent. Usually in daily life, when you're just dealing with parametric probability density functions, you don't have to invent the whole thing. Here, I'm just discussing it because we have to discuss a Gaussian random field, or random fields in general. Okay, that was a long answer, but yeah. So it's art, right? So it's not. So you can, and it's art and creativity. So and usefulness, these things. So you can always invent these kind of abstract things, which are kind of creative, but they have to have some use. Otherwise, people will think you're crazy if you cannot say what the use of this is. And they will not understand what you want from them. Good. To maybe deepen a little bit the idea of distributions, I want to show you a little bit of notation that we also will need specifically in the p-value, so that we specifically will need when talking about random fields for p-values, which also should which should ring familiar. So I think you've seen, of course, things like p x equals something. You've seen something like this. So the probability of x taking on a value a, and then this was defined, I mean, you did it in your table, this was defined as 1/10 or something. So it had some meaning. There we were actually talking about probability mass functions. Currently we're talking about probability distributions, so we're not completely talking about the same thing, but at least something like this notation you have seen. Now, how is this notation? What does it mean in the current context of probability spaces and so on? What something like this means x equals a, or another example that we actually will need quite a lot in our random field p-value business is x being larger than some value. And this value a, it will later be called u and will be the cluster defining threshold, and it will be the thing that made a lot of buzz in 2016 and until now. So we actually will deal with this, and it's on people's mind when talking about fMRI. In the context of probability distributions and probability spaces, what these things stand for are the sets omega in omega for which x omega actually equals a, and here these are the omega in omega for which x omega is larger than a. So this now refers to, maybe I should have told you that before, this refers to that x is actually a real valued random variable and a is a real value. Yeah? So a is in R. Of course, you can always make this more abstract and not consider real values, but maybe a mapping from a set of functions to another set of functions, or from a high-dimensional space of functions to an n-dimensional space. But the basic case that we are interested in is, of course, real-valued random variables. Actually, also for the random fields. So the random variables that will make up our random fields are real-valued, because essentially at each voxel you only have one value and not a vector. So this is what this means, and then from this it follows then essentially that, for example, this thing x equals a, that this means this So I briefly try to explain again what this should mean. So here we have the distribution of x, which is a probability measure. And we now talk about the value that it assigns to a specific set in the range of the random variable. And this range, if we have the real line, then the real line is the range, and there might be an a. Now this thing px x equals a, this is defined from the setup that I've told you before in terms of the probability measure of the underlying probability space as the p without the x, so the p of the underlying probability space of those omega in omega, so that's the whole omega, and this is now, let's say, the omega and omega that map onto A, that map onto A. Yeah. And this kind of notation then can be generalized, of course, to larger than, smaller than, and also just an element of S, which you find on page 11. Of the handout. What is? Okay. So I think the last thing that I want to do just for today, so next time we then can use all of this to define a random field, so that will be the first thing next time. The last thing that I want to just mention and define is the notion of a distribution function, which you should not confuse with neither a cumulative density function nor with a density function. You should just learn a new term, which is called a distribution function, which we will need extensively in random field theory-based p-value. A distribution function of a random variable in this whole setup that we discussed, of a real valued random variable. So x is a mapping from omega to r, is defined as a mapping from the real numbers to 0, 1, and each real number gets allocated a value of the distribution function x that corresponds to the value of the distribution of x in this kind of notation that we've seen before, that the value that x takes, so the random variable takes on, is smaller or equal to x. Yeah? And one can show, using mathematics, that distribution functions fully specify probability distributions. Yeah? If you write down the distribution function, you have equivalently written down the probability distribution. The other way around, if you define a probability distribution, then also the distribution function is fully specified. And there's at this point not much else to say about this. Distribution function will come up again, so we will discuss them then at that point when they are important. Good. I think in terms of context, I stop here. There is more on expected value and covariance in the script. I will not go over that in the beginning of next class. I will go over that when we talk about the expectation function and the covariance function of a Gaussian random fields, because this is when we need it. So this means so actually the study questions for next time are only the first 5 questions from the study questions that are there. There is also, and I want to mention that and point it out, there is this calculus appendix. It was there last week and it's still there, but now it's really just called appendix. As said previously, you should go over that on your own. Maybe if you have some people, so there are some people in your class that know all the content of the calculus, because, so for example, Lena, because this is basic undergraduate calculus as you learn it in every technical discipline. And it's actually also the same calculus that you learn in school, so it's not, maybe apart from the multivariate aspects, it's really the stuff that you learn in school, so you should go over it on your own. And at one point I will also in the active participation ask some questions from that part, and they will also be part of the exam. So this is basic calculus. It's like calculating the derivative of x squared. And the main point why we have that there is because, and why we also need it, is because we will see this notation at one point of the course, and I don't want you to go all crazy about this notation, but this notation is really straightforward. So please work on the calculus as there are millions of online tutorials for this stuff that is in this part of the basic calculus. Ask your classmates who are familiar with this basic calculus. Then I have to say it's not that badly written, I think. So it's fairly, so if you just go over these things, memorize them, then you are all set. So there's nothing that really should be too confusing. So please look into that. Yeah. Good. Any other questions for today? No? Good. Then let's stop here and start next Monday with random fields. Goodbye.